Good morning, students. Welcome to the lecturing class on control engineering subject. So today we'll start with the fourth module. So in that we'll take the bit which is Bode plot. Okay. So the basic of any frequency response is to plot the magnitude m and the angle phase angle pi against the input frequency omega. But when omega is varied from 0 to infinity, there is a wide range of variations in magnitude as well as the phase angles. So hence it will be difficult to accommodate all such variations in the linear scale. So for that reason, the scientist H.W. Bode has suggested a method in which logarithmic values of magnitude are to be plotted against the logarithmic value of the frequencies. Okay. So such plots we can call it as logarithmic plots, which allows us to show the wide range of variations in the magnitude on the single paper. So it is a method in which the logarithmic values of magnitude are to be placed or plotted against the logarithmic values of the frequencies. So in general, Bode plot is consisting of two parts. One is magnitude expressed in logarithmic values against the logarithmic value of the frequency called magnitude plot, and similarly the phase angle in degree against the logarithmic values of the frequency called phase angle plot. So if you see the definition of both that magnitude plot and phase angle plot, so there the x-axis is same, that is, it is the logarithmic value of the frequency only. Okay. So in that, first one is the magnitude plot. So here the magnitude can be expressed in the logarithmic values by finding out the values of 20 log to the base 10 to determinant of g j omega, g of j into omega, which has a unit as a decibel and denoted by dB. So for Bode plot, determinant of g of j omega is equal to 20 log to the base 10 determinant of g of j omega dB. Similarly, the phase angle plot, the angle of g of j omega is to be expressed in degrees, which is to be plotted against the log of omega. That is, along this axis, logarithmic value of the frequency, and here the phase angles in degree. And here it is along this x-axis, it is logarithmic value of frequency, and along y-axis it is the magnitude value, which you have determined by using this 20 log to the base 10 of g of s. Okay. So then there are some standard factors which you need to understand before starting with the actual plot of the frequency versus magnitude and then the phase angle versus logarithmic value of the frequency. So here the main aim of this Bode plot is to represent the wide range of variations in the magnitude on a single paper. So now in a given transfer function we have many terms. So for each factor, the procedure to be obtained to have the Bode plot, so it can be divided into the following steps. The first step is replace s by j omega in your transfer function to convert it into frequency domain. Find its magnitude as a function of omega. Express the magnitude in decibels, that is dB, by using this equation, that is 20 log to the base 10 determinant of g of s into h of s. Wherever s is there, I am replacing that s by j omega. Then find the phase angle by using tan inverse of imaginary part divided by real part, and this angle should be in degree. Then with the required approximation to plot the magnitude in decibels and phase angle in degree against the logarithmic value of the frequency by varying the frequency value from 0 to infinity. So in that, let us start with the analysis of the basic factors one by one. So the first factor is system gain, that is k value. So it can be written as m into 20 log of k So for this, the slope will be d of 20 log k divided by d of 20 log derivative of 20 log of omega. So it will be 0 because this k will be constant here, and phase angle will be tan inverse of imaginary part divided by real part. Since there is no imaginary part, we'll take that one as 0. K is constant, so 0 by k. So tan inverse of 0 by k will be 0 here. Then the second factor is it is a pole or a zeros at origin. So for this it is j omega raised to plus or minus n. That means this j omega means it is yes. Okay, in your transfer function you are having the terms in the form of s. So I am replacing that s by j omega here. Okay, so for this the magnitude m will be 20 log of determinant of j omega plus or minus n, or we can write it as plus or minus 20n log of square root of omega square plus 0 because there is no real part. Okay, so root of omega square will be omega only, so we will get it as plus or minus 20n log of omega. Okay, so from this you need to identify the slope. So slope will be plus or minus derivative of 20n log omega divided by derivative of 20 log omega. So from this we can say that the slope will be plus or minus 20n per decade. Okay, and if n equal to 1, the slope will be plus or minus 20, and phase angle is given by plus or minus tan inverse of omega by 0. Omega by 0 means it is infinity, so the value is 90 degree. Angle is 90 degree here. And if the slope is plus 20, that is if the term is in the numerator, that is if it is a 0, that time you can consider it as a plus 20, and it is starting from 0 and ending at 20. Similarly, if the slope is minus 20, that is for the terms which are in the denominator, that is for the poles, the slope is going to be minus 20. So it is starting from 20 and ending at 0. So this is the plot. This is for plus 20 and this is for minus 20. So the third factor is simple pole or zeros of first order. So if you are having the terms like 1 plus s or 1 plus 5s like that, we can call them as a simple pole or zeros of first order. So that is 1 plus t of j omega raised to plus or minus n. So magnitude will be 20 log determinant of that term, or plus or minus 20n log of root of 1 plus t omega whole square. Okay, because here the real part is 1 and imaginary part is t omega. When omega to t is less than 1, that time we can take it as m equal to plus or minus 20n log of 1. So log of 1 will be 0. So the magnitude will be 0. If the omega t is greater than 1, that time the magnitude will be plus or minus 20 log of omega t. So here one extra term will come, that is a break frequency. Before that, in this equation, if it is a for this one also the slope is minus 20 dB per decade, as again for every decade, that is for every decade, the change in omega, the magnitude still decreases by 20, that is the slope is minus 20 here. Thus for the low frequency, magnitude plot is 0 dB line, while for the higher frequency it is a straight line of slope minus 20 dB per decade. So now it is necessary to find the frequency omega, which separates the frequency range into low to high. This is the value of frequency at which straight line of slope minus 20 dB in high frequency range intersects with the 0 dB line in the low frequency zone. So such an interaction takes place when this 20 log omega t is equal to 0 dB, that is omega t equal to 1. So this is a frequency at which the change of slope from 0 dB to minus 20 dB decade occurs. It's called as break frequency, or in some of the books they have called it as corner frequency. Okay, so that is when this omega equal to 1 by t that is omega value is 1, so 20n into log of 1 equal to 20 plus or minus 20n into log of t omega. So from this we'll get the break frequency or corner frequency as 1 by t, and the phase angle is plus or minus tan inverse of t into omega divided by 1. So here whenever we are writing this plus or minus, if the term is in the denominator, you have to take it as with negative sign. If the term is in the numerator, you have to take with positive sign. Remember that. So if n equal to 1 and break frequency omega b is also equal to 1, that is till omega b equal to 1, slope is 0. After omega b equal to 1, slope will be minus 20 dB. Here. Then the fourth one is a quadratic factor. That is, if the given term is in the form of s square plus 2 zeta into omega ns plus omega n square raised to plus or minus n. This is the standard form. So for that the magnitude will be 20 log of that term, replacing s by j omega. If you simplify that, you will get m as 20n log of root of 1 minus omega square by omega n square whole square plus 2 zeta into omega by omega n whole square. Here, when this omega by omega n is less than 1, the magnitude will be 0. If it is greater than 1, the magnitude will be plus or minus 20 log root of omega by omega n whole square and again square. So you will get it as plus or minus 40 log of omega by omega n. That means till the break frequency omega b, the slope will be 0. After that, the slope will be plus or minus 40 decibel per decade. Again, you have to take plus 40 if that term is in the numerator, that is for the zeros. You take minus 40 if that is in the denominator, that is for the poles. You have to take it as negative sign. And the phase angle is given by plus or minus tan inverse of 2 zeta into omega by omega n divided by 1 minus omega by omega n whole square. If this omega by omega n is greater than 1, that time pi will be 180 minus of this. Okay. So here you need to remember this table. For the constant term, the first column is for the terms, second is for the slope, third is for the break frequency, and it is for the phase angles. If in the given transfer function, if you are having the constant, for that slope will be 0, there will not be any break frequency, and phase angle will be 0. If there is a simple pole or 0, either it may be s or 1 by s. So for that it will be plus or minus 20n is the slope. That is, if it is in the numerator, that is for the zeros, you have to take the slope as 20. For the poles, you have to take the slope as minus 20. And the angle will be plus or minus 90 degree. And similarly for the first order poles or zeros, that is 1 plus t of s is the standard format. So it is plus or minus n. So the slope will be plus or minus 20n and break frequency will be 1 by t. That t is this one. And angle will be tan inverse of t omega divided by 1. Similarly, if it is a quadratic pole or 0, that time the slope will be plus or minus 40n and break frequency will be equal to omega n, and the angle will be tan inverse of 2 zeta into omega by omega n divided by 1 minus omega by omega n whole square. And if there is a term like e raised to plus or minus as, that time for that also there will not be any slope or break frequency. The phase angle you have to take it as a into omega. Then the next thing is, we'll try to understand some of the basic definitions or the frequency response specifications. So the first one is bandwidth. So it is defined as the range of frequency over which the system will respond satisfactorily. It can also be defined as in one more way, that is as a range of frequencies in which magnitude response is almost flat in nature. So it is defined as a range of frequency over the magnitude of closed loop response and does not drop by more than 3 dB from its zero frequency value. Then the second one is cutoff frequency, that is omega b, and it is denoted omega b. So here the frequency at which magnitude of closed loop response is 3 dB down from its zero frequency value can call it as cutoff frequency. That is, the range 0 to omega b is nothing but the bandwidth of the system whose frequency response is known. Similarly, the bandwidth indicates the speed of the response. It indicates the ability to produce the input signal, and it is inversely proportional to the rise in time. And larger the bandwidth means small rise time means fast response. Okay, so that is the reason for a system it is better to have the good bandwidth. Then the third one is cutoff rate. So it is the slope of a resultant magnitude curve near the cutoff frequency is called as cutoff rate. Then the next one is resonant peak, denoted by MR. So it is the maximum value of magnitude of the closed loop frequency response. The larger the value of resonant peak, more is the value of peak overshoot of the system for the step input, and it is a measure of relative stability of the system. Then the next one is resonant frequency. And it is denoted by omega r. So here the frequency at which the resonant peak, that is MR, occurs in a closed loop frequency response is called as resonant frequency, and it is basically inversely proportional to the rise time. And these are the general specifications, but the specifications which are most important for the stability and relative stability analysis are the gain crossover frequency, phase crossover frequency, gain margin, and phase margin. Okay, so the next one is the gain crossover frequency. Here it is the frequency at which magnitude of G of S into H of S is the unity, that is 1, is called as gain crossover frequency. Generally, the magnitude of the transfer function is expressed in decibels, and this dB value of 1 is 20 log 10 1 equal to 0 dB. That means it can be defined as frequency at which magnitude of G of S into H of S is 0 dB, that is at omega Gc. Then the next one is phase crossover frequency. The phase crossover frequency. So here it is the frequency at which the phase angle of G of S and H of S is minus 180 is called as phase crossover frequency, or it is a frequency at which phase angle is G of S and H of S is minus 180. If that phase angle is minus 180, so at that angle, whatever the frequency you will get, that frequency is known as phase crossover frequency. The next one is the gain margin. We have already studied the root locus. So in that the gain K is increased, the system stability reduces, and for a certain value of K it becomes marginally stable, except the first and second order systems. So the gain margin, basically it is defined as margin in the gain allowable by which gain can be increased till the system reaches on the verge of instability. That is, the positive gain margin means such increase in K is possible before the system becomes unstable, and the system is stable, and the negative gain margin means K is greater than the K margin, then the system is unstable. So K is required to be reduced to make the system stable. Okay. Then the next one is phase margin. So it is similar to gain. It is possible to introduce a phase lag in the system, that is negative angles, without affecting the magnitude plot. That is, the basic definition is the amount of additional phase lag which can be introduced in the system till the system reaches on the verge of instability is called as phase margin. Again, here also, if the positive phase margin means such negative angle introduction in the system is possible before system becomes unstable. Such system is a stable system, while a negative phase margin means the present negative phase lag should be changed by adding a positive angle, hence the phase margin is said to be negative and system is unstable. So these are the some of the basics of the Bode plot. So here you need to understand what do you mean by magnitude plot and what do you mean by phase angle plot. For that, you need to understand the standard factors and what are the steps involved to analyze those standard factors. So that is how to take or which slope you have to take and what is the angle when the for the factor constant, that is for the system gain. If there is a pole or zero at the origin, how to take the slope and angle, and if the pole is a simple pole or zeros of first order, how to calculate the break frequencies or corner frequencies and how to take the slope for those things. Then if the factor is a quadratic factor, then that how to take the slope and how much you have to take the slope and what will be the magnitude and how to calculate the phase angle, and if that omega by omega n is greater than 1, then how to calculate the phase angle, that is 180 minus of that angle you have to take. Similarly, you need to remember this table, okay, for different terms, what will be the slope and how to write the frequencies and how to get the phase angle. After that, you need to understand these basic definitions or frequency response specifications, you can say. So try to remember these basics definitions. More important definitions are this gain omega gc, that is gain crossover frequency omega gc, trace for crossover frequency omega pc, and what do you mean by gain margin and what do you mean by phase margin. So from the next class onwards, we'll start with the problems, that is how to construct the Bode plot by using these steps. Okay. If you have any doubt, you can leave the comment in the comment box. Thank you.